Those of us that study meteorites, or rocks from space, we're really at the mercy of what falls from the sky. Meteorites come from asteroids, and asteroids largely occur between the orbits of Mars and Jupiter in our solar system. But every now and then, some of those orbits get perturbed, and one of those asteroids can be sent into near-Earth space. Asteroid Bennu is a near-Earth asteroid, and we were able to sample that asteroid and bring back a piece of it here on Earth. Right? We went into orbit around the asteroid, we imaged it at high resolution, we did spectroscopy on it, so we know its composition really well, and we knew all of that information before selecting a sampling site that we picked and plucked some of this material off of Bennu to bring it back. So we have all that contextual information now that will help aid us in studying the sample here in the laboratory and really studying it at fundamental levels and telling the story on the origins and history of Asteroid Bennu.
I think one thing that was really fascinating, even from the really early stage, from the quick look, when we first got a look at the sample, is how similar our initial observation were to what we expected the sample to be from all the remote sensing data that we had from the spacecraft. For example, all the amount of water, so meaning that the amount of water-bearing phases that we found in the sample. We found a lot of clay minerals, the amount of carbonates, the amount of carbon that we saw in the sample. So we directly found all the key observation that the spacecraft did while the spacecraft was basically orbiting around the asteroid. We got sample initially from the quick look sample that we brought back to the university, and we also got recently allocated aggregate sample of particle on the order of a few hundred milligrams, and that our students and postdocs are currently studying in the lab. The initial step was basically a triage, going to the particles, documenting, getting optical images of the sample, seeing what they look like, classifying the sample, so we can actually decide which particle will be studied for what particular purpose.
When we look at that level of scale, we're talking about we can do measurements that are down at the nanogram and picogram level to get really, really detailed, rich information and insights into the origin of these materials. The level 1 requirement for OSIRIS-REx was to bring back 60 grams. You could do the simple math, divide 60 grams by a few nanograms and figure out how many of these samples you could look at. You could spend the rest of your career looking at this stuff. But the reality is, of course, most of the material that we will get allocated to us will be looked at with a bunch of different instruments that are spread across the science team, that are spread across the world. Science team only gets 25% of it, and then there's a significant fraction of the sample that's going to be preserved for future generations. Much like the Apollo missions brought back moon rocks, and we preserved a large fraction of that for subsequent generations of scientists to look at, and we're still doing groundbreaking science on lunar samples that were brought back in the late 60s and the early 1970s. Similar things will happen someday in the future. They'll have instruments that surpass the instruments that we have now. So to NASA's great credit, they recognize this, and this was implemented as part of the curation plan. And I think it's a really important legacy for NASA and for the mission, and of course it will be a valuable resource for future generations.